Hardware engineering teams have a tendency of, here, I'll show you, just going off whatever data they can find, like on DigiKey or Mouser or whatever, about an LED when they're choosing one for some lighting part of their project. And that's a good place to start, but you really need to go into the datasheet to really understand what kind of source you're working with, and a lot of these teams don't. I think it's probably because it's a bit intimidating, all the information that's in there, so I'm going to go through over a few videos going through a datasheet, going through the type of info that we see on like DigiKey, Mouser, so that hopefully it's not scary and you know what you're looking at and you feel more comfortable going through all these like dozen pages of random gibberish. And also, so you can verify the information that you see on those summaries on the vendor sites, because a lot of times that information is wrong. So here we are in DigiKey with our white LED lighting results if we're looking for a white LED. If we scroll to the results, we'll see a bunch of different pictures, what they look like. That's nice. And then, oh, there's the data sheet over here, but most people are going to just skip right over that. That's okay, we'll get to that later. And let's look at the other data that's in here. So there's how many are in stock, there's a price, those are all important things. But then over here we start to get to the technical information. Now they have color, and right next to that they say CCT and K, whatever that means, it's Kelvin. The color can be warm white, cool white, neutral white. What does that mean? And then these numbers, what do those mean? Well, it means this. And so this is the warm white. These will be like 1,000 to 3,000 Kelvin, maybe 2,700 is definitely warm, 3,000 is getting into like neutral. This is all neutral here, 4,000. Over 4,000 is kind of into cool, which is most of these. You usually won't see 90,000 Kelvin for your interior lighting. It usually stops at maybe 45, 5,000. Some sterile environments might get into like 6,500 K, but that's what that means. If you're looking for like a normal neutral white and you want it to look like that, then these are the numbers you have to shoot for with that CCT in Kelvin. Or if you want warm, you go lower. If you want cool white, you go higher in number. Then it has flux at 85 degrees C. So this is how many lumens usually that we're talking about. Sometimes it'll be in a different unit of measure with radiometric units, but usually with white lights we're talking about photometric units, and this will be in lumens. Now, why don't all of these have a value for 85 degrees C? I'll talk about it in the next video. Part 2 of LED datasheets, and we're going to talk about why you don't get flux values, so lumens usually, for 85 degrees C from different vendors for LEDs. But you'll more commonly find 25 degrees C. Why is that? It's because when you first turn an LED on, it's going to be around 25 degrees C, and most manufacturers will take a measurement right then of how many lumens are coming out. And it's really high because as this is staying on for a while, it will warm up. And as it warms up, not as many lumens come out, or watts. So that 25 degrees C instant on measurement is going to be a lot better looking for the vendor than the 85 degrees C one, even though in most applications you want to know how much light you're getting out after it's warmed up, after you're not getting as many lumens out of that. Most applications are going to care about that 85 degrees C number, because if it's a lamp, a luminaire, a light for your house, a restaurant, an office, the parking lot, or the exterior lighting on your vehicle, those are all designed to regulations that test at 85 degrees C-ish, wherever thermal stability is. So after it's warmed up and it's producing the least amount of light. If your product is one of those categories where you care about how much light you're getting out at 85 degrees C once it's warmed up, once it's the least amount of light that you're gonna get ever out of that product, then you need to be looking at this number for how many lumens you're getting out to start with in your system, not this number, the 25 degrees C. But because it's more common to have the 25 degrees C value for how many lumens are coming out, sometimes that's a better way to compare different LEDs to see which one is most efficient. Scrolling past lumens, then we get to current and forward voltage, and usually they're going to display the typical values for these, even though, especially with forward voltage, there's going to be a range. Next, we have lumens per watt, and this is important when you're trying to make an efficient luminaire, an efficient lighting fixture. You'll want the highest number of lumens out of that thing per watt of energy that you're putting into it in the beginning electrically. But even here, there's a bit of confusion because, well, how many lumens are we talking about? Was this at the 25 degrees C value or the 85 degrees C value? So let's do a little math to try to figure out where they got this 122 lumens per watt from. So if we multiply these two together, the milliamps and the volts, will get watts, so 0.06 times 3, 0.18 watts. We'll put that on the denominator and multiply by 22 lumens. And we get 122. So that's where they got it from. They're using the 25 degrees C amount of lumens and using this typical watts from these numbers. But if you care about efficiency at 85 degrees C, it's going to be a lower number. Continued in part 3. Part 3 of LED Datasheets, and there's one more thing that you should know about efficiency before we move on. If you're on DigiKey or whatever, you can sort by lumens per watt. That's efficiency. So you could sort by getting the most amount of lumens per watt of electric energy going in if you wanted to. But caution, danger, Will Robinson. If you do that, it will sort by whatever number is in this column, and the numbers in this column are based on different things. In the last video, we calculated that this first row had 122 lumens per watt, and that was based off of the lumens you get out at 25 degrees C, which is best case scenario. It's before it's warmed up, and no thermal derating has happened so far. But if you go down to this row, the 165 lumens out of it, that is from 85 degrees C. So that's when it's warmed up. And they don't have a value in here for the 25 degrees C amount of lumens that you get. So the efficiency that they came up with for that column is 163 lumens per watt. And that is lower than if they had calculated it at 25 degrees C, how many lumens you're getting out at that point for the same amount of electrical energy, the same amount of watts in. So it's quite possible that this could be the best choice for your hardware with what you're trying to build, but if you sort by highest efficiency with this column, you might not see it that way. It might not even show up in your results because the ones that are rating this by how many lumens you get at 25 degrees C are gonna show up way higher in the results. Even though in reality, this might have a higher efficiency. But now that you understand the difference between how many lumens you get out at 25 degrees C versus 85 degrees C, you can look at this compilation of results on DigiKey or Mouser, and you can understand that difference and not get fooled. Moving on to CRI, Color Rendering Index. This is another one that you're only gonna really find for white LEDs, and it's another way of classifying the color output of that thing. So you'll see 90, 70, 80. What does that mean? That number you get for CRI is based on a contrived test to quantify how well certain lights reproduce certain colors. And one of the most important ones is red, because that's a real easy one to screw up. What do I mean by screw up? Metamerism. And here is an example of metamerism. So in both of these boxes, we got the same two balls here. And in this lighting, it looks like they're the same color. In this lighting, they are clearly not the same color. Well, why does that matter? High CRI is important for aesthetic reasons, but also for machine vision applications. More in part 4. Part 4 of LED Datasheets, let's talk more about CRI, Color Rendering Index. Here's another example of metamerism where we have two balls under like an incandescent light indoors, and then under sunlight, what does that look like? And here under sunlight, you can see that they're two different colors, but indoors, under your light bulb, they look like the same thing. Sunlight has a CRI index of 100. It's the best thing to put your makeup on under. And 100 is the highest value you can get of CRI. Everything else is rated against sunlight. And the lower the CRI index number, the worse the color rendering. So this would have, I don't know, maybe like a 70 CRI. Now, if you're building a robot that has machine vision, that has a camera where the camera is helping it do things, if that camera uses color to differentiate between objects, you need your light source to also be able to differentiate between objects, between the different colors of those objects. So in that case, CRI value would be very important for that machine vision application, but maybe not for all. If you're not trying to differentiate between objects based on their color, then maybe you don't need a super high CRI value for your robot. Now going back to the data on DigiKey, we see the CRI values here and 90, 70, 80. So 80 would be like a typical light bulb that you'd get, maybe an LED light bulb for your house. 70 would be bad. That's really not good color rendering. You wouldn't want that in your house. And then if you bought something with a high CRI value, usually that's 90 or above, again, with 100 being the ultimate best because that is sunlight. Next, moving on to maximum current. This is usually just the maximum that they have on their data sheet for how many lumens you'll get out at that current, but that does not mean that you should drive that LED to that current. So for this top one, the maximum current is 128 milliamps, and let's go over to what they tested it at, which is probably typical at 60 milliamps. Normally, manufacturers of LEDs are going to test their LEDs around that typical current value of, for this case, 60 milliamps, plus minus a little bit, but they're not going to drive it at the absolute maximum and then have it run all day long at that maximum value and see if it's still okay, because it probably won't be. Because once again, as you let that LED run, you are heating it up, and if you are pumping in twice as many amps as you normally drive it at, then that's heating it up even more. The times when you would use this like absolute maximum would be if you're just flashing the light, maybe at the same time as you're taking an image. So it's only going to be at that amperage for like a split second, not for 20 hours a day. In part 5, we'll talk about viewing angle. Part 5 of LED Datasheets, and we left off at viewing angle. This thing, we see 110, 120, 115. What does it mean? If you thought it was the largest angle that you could still view light coming from the LED, you'd be wrong. Yeah, it's a horrible name. Instead of viewing angle, you might hear the term beam spread or beam angle, and usually these all mean the same thing: full width, half max. And when it's called full width half maximum, it might also be abbreviated to FWHM. Stay with me, it's not gonna be that hard, I promise. If this is our LED, we're gonna have rays coming out all over the place. But let's simplify that by just looking at this ray fan to represent the angles that the light is coming out at from the side. If the ray is coming right from the center and it's coming straight out this one, that is called 0 degrees. And you can have rays coming out from all the way down to plus 90 degrees down here or minus 90 degrees down here. So there's a whole 180 degree spread, usually. Now let's do a ray trace of all the rays coming out of an LED. If we make a receiver that's really, really big all the way around this LED to catch the rays, here's what those results look like. This is a polar plot. We're usually not used to seeing those unless you're in pre-calc right now in high school. But it's a good thing to get familiar with because oftentimes this is how beams are represented coming from optics or LEDs or both. So right down the center, it's kind of upside down, but we have 0 degrees. So that was that center ray that was coming straight out the top of the LED. That's how much light we have coming from there. And then there's 90 degrees to the side of the LED, and that's 90 here, or you can go negative 90 degrees on that other side of the LED, and that's negative 90 degrees here. Now here's what full width half maximum means. Here is the maximum at 0 degrees. It's about 200 candela, 200 CD. What is half of the maximum? It would be about 100. So if we go to 100 and we go to either side, we'll see that's at around 60 degrees. So it's plus minus 60 to get to half of this value that's the highest at 200. So 60 this way plus 60 that way is 120 degrees. So the full width half maximum of this LED is 120 degrees, or beam spread or beam width. Although that's more if you're talking about lenses or reflectors. Now you'll notice if we go, okay, here's 60 degrees, that's where 100 is, that's half of the maximum. But wait, there's still all this light coming out, as we saw from the CAD of the LED. Between 60 and 90 degrees, there's still light coming out there. So it doesn't mean there's no light beyond 120 degrees, if that's the full width half maximum. It's just full width at half of the maximum. A little more less common would be full width tenths of a max. That's another way to describe a beam. And that would be same way that you calculate full width half max, except it's a tenth. So if this is 200, then a tenth of that would be 20. And so we want to go down to here and see where we're hitting that there. And it's about, 75 degrees maybe, plus minus 75 degrees. Full width tenth max is a good way to understand like how far out do you have to go to capture most of the energy in the beam. If you have to go all the way out to 98 degrees, or not 90, 89 degrees, then it's not a very tight beam. There's a lot of light that probably isn't going to be used because there aren't many applications that actually need light at 90 degrees. Another term you should be aware of is that this full width half max of 120 degrees, it can also be considered a Lambertian distribution. Scatter can also be categorized as a Lambertian distribution. And I can get a lot more into that, but basically it just means that if you have a source and its emitting amount of light, you're going to get so many light rays divided by this surface area. And then as you turn it, this surface area of this yellow dot gets smaller, and the light that reaches your eyes is going to get smaller in the same proportion that this surface area is getting smaller. Well, effectively, it's the same brightness or perceived brightness. But just know that when you see Lambertian distribution, usually they mean about 120 degrees full width half maximum. Next up is mounting type. That's how you stick it on the PCB board. And then next you see package case and supplier device package, then size dimension. These are all about the physical size of your LED or COB or CSP or whatever you're working with. And if you notice with these metric numbers, let's take this 3030 metric, and then the supplier device package, that's 3030. You'll also often see one of these numbers in the LED like name, the part number, and what that often means is that it's a 3mm by 3mm. And then this 35 by 35 or 3535, sorry, that would be like 3.5mm by almost 3.5mm. So sometimes that can be a little hack to figure out what size an LED is before opening up a datasheet. And then in the very last column, we have height, which is height. Okay, so finally now let's look at a datasheet. Let's first look at this Cree X-Lamp Gen 3 LED. The Gen 4 doesn't have datasheets yet, so we'll go with this one. And here we go. So there's two different versions, first off, and you gotta make sure whenever you're ordering one that you know which one you have, because sometimes, again, the vendors that are like DigiKey and Mouser, they might give you one and it looks like it's labeled as the other one. So high density for Cree has the bubble, usually this lens on top, and the high intensity is flat on top. So even the pictures are important on a datasheet. On the first page, they're gonna have a summary of the most important points, but this should all still be later on more detailed in the rest of the datasheet. And this datasheet is 49 pages long, so we're probably not going to go through every page, but we'll hit the most important stuff. On the second line, we see viewing angle that we just went over, and that FWHM in parentheses, which we already know now, is full width, half maximum. Good job! And then they're telling you that they're measuring that in degrees and that the typical number is 120. So same as the example we just looked at. And then we see DC forward current and forward voltage, and this is how much juice it's gonna need to draw in order to turn the thing on. And then we have those numbers in milliamps and volts respectively. At the bottom is LED junction temperature, and that has a maximum value of 150. So if you go over that, shit's gonna start to break. Don't do that. Next page, we're getting flux characteristics specifically for that high density LED with the dome on top. You gotta make sure you know which chart you're looking at for this one, because there are two types of LEDs for this datasheet. But if we look closer, we can see that this is for nominal CCT of 5,000. And then if we go down to the next page, there's a different chart. You're gonna get different amounts of lumens out for 4,500K, so a less cool white. And then for 4,000K, yet a different set of lumen values that you can expect. And 3,500K, 3,000K, they're all different, all the way down to 2,700K. So why is that? So to get white light with these LEDs, it starts with a blue LED and then some phosphor coating this yellow stuff is put on top to knock it down into the other colors of the rainbow so that it mixes together and gives you white. The more this phosphor has to punch the blue in the face and knock it down a peg into the other wavelengths, the more energy it loses. So those cool 6,500, 5,000 K whites don't have a whole lot of phosphor knocking down its energy compared to like really warm 2,700 K like candlelight light. So with the really bluish white, you're gonna have more energy coming out in lumens for every watt of electricity you're putting in, because it's not getting eaten up a lot by this phosphor. And that's important to know for designing and picking LEDs, because if you don't actually need that warmer color temperature, then you probably don't want to lose energy that way. Usually people are trying to get the most efficient option possible, and that's to go the bluest white as possible, or the highest Kelvin. On the next column, we see CRI, which we've gone over already, 70, 80, or 90, with 90 being the best one that they offer here. The different CRI values have the same effect as going to a warmer color temperature. When you're increasing the CRI, the color rendering index, you're decreasing the energy. So this 90 CRI is going to have lower lumen output than the 70 CRI. Next, we'll talk about binning. Oh boy! Part 6 of LED datasheets, and we're picking up with binning, or LED bins. The last part we saw that different color temperatures are going to have different minimum lumens, different minimum luminous flux coming out. So if we look at this 4,500K color temperature LED and we go to 70 CRI, then we'll see the lowest bin for the flux is this J2 group that's going to give us 1,040 lumens. But if we go to the same CRI for a different lower color temperature, 3000K, 70 CRI, then its lowest bin or lumen output is going to be 970 lumens. So you need to know which bin you're getting when you're testing out an LED, not just color temperature and CRI, but is it K2, J4, or J2? And those are just the minimums that are listed on that data sheet. So it can go even higher than that. There's a very big range in the amount of lumens you could be getting out for the same amount of power when you're taking an LED and sticking it into your system. But why? Haven't they figured that shit out yet? It helps if we understand how LEDs are fabricated. So normally you'll have like a big wafer, and the wafer is gonna have a bunch of different coatings that the manufacturer's gonna try to put down really, really precisely and thinly on that wafer. And they're coating this whole thing, but this whole thing is actually gonna be a whole bunch of different LEDs that they will later cut into pieces. But the differences in thicknesses that can change how an LED functions are so minute that they can't just force them all to be one color temperature, one efficiency across all these different LEDs. So they just kind of like roll the dice and see how each of these spots wind up. If this little block has a few more atoms of phosphor or gallium or whatever is in the chemistry to change the colors for that formulation, compared to this one right next door, it might be a different bin of CRI. So after all the coatings are applied, these things are diced up, and then each one is individually packaged into like a fully functioning LED diode, and then they're flashed on and instant on to measure the color temperature, the CRI, and how many lumens are coming out. So let's pretend we're the LED manufacturer and we just got one of these LEDs fresh off the lithography press or whatever, and it ended up being 4,500K, and it was 70 CRI, and when we flashed it on an instant on, so that would be the 25 degrees C column, we got 1,250 lumens. In that case, it's more than the minimum for the J4 group, but it's less than the minimum for the K2 group. So that would be in bin J4. But it could have also been much higher than these numbers, because these numbers listed are only the minimums for each of these groups, depending on their color temperature and also their CRI. If we scroll to the bottom, there is more information. The way down here on page 31 of 49, we can find the performance groups of luminous flux. These are the different bins they have for how many lumens are coming out. And if you notice, the smallest could be 635. That's the minimum for the lowest bin, which is E4. Or it could be a maximum of 1,380, which is the maximum luminous flux for the highest bin of K4. So that's like almost, well, maybe more than twice as much. Twice 635 would be 1270. So yeah, that's more than twice as much that you could get on the high end versus from the low end. This is why optical engineers who specialize in illumination know this and will design around, if they can, the lowest flux bin for an LED. Sometimes there's no way around it. You just have to specify a higher flux bin. So maybe it's a machine vision application and the robot just can't see unless there's a minimum of 900 lumens coming out. So in that case, then we have to specify H2 group or higher. But there's a caution with that. It's generally not good to have to specify a higher bin because one, it costs more, and two, it's going to be introducing potential supply chain risk because it happens randomly how many LEDs that they get yielded out of each batch that they manufacture for different group codes of flux and CRI and color temperature. Manufacturers can't completely control the supply of each of those bins. That means if you specify a bin as a minimum bin that you can order and there's a supply chain interruption, you don't just wait until the manufacturer is able to turn on the supply again. You have to wait until first the supply is turned on again, and then again, you wait until they have enough of whatever bins you specifically need. And you might be waiting in line behind bigger customers that order hundreds of millions of products a year. They're gonna get their stuff first. But if you really do need that higher bin LED in order for your system to work, you can specify it. Another caution you need to know if you're developing hardware about LED binning is if you're pulling in pieces to use in a prototype, you need to know exactly what the hell you're working with. Exactly. At the very least, you should know the specific flux bin, please. Because if you put together a prototype and you use that as proof of concept, and it's, a flux bin that's on the high end, you get lots of lumens out of that LED. And you're like, yay, my system works, my robot can see. And so you're like, okay, this LED is fine, it totally works. Well, that bin worked, but will any of the lower flux bins work? You don't know that. Now it's possible for you, if you know the bin of the LED that you're using, to lower the current to match that lower lumen output for the lowest flux bin possible for you to be getting when you're manufacturing this thing, and test that out and see, can I still have a system that works with this lower amount of light, and prove the concept that way. But if you don't know what the hell you have to begin with, this is very difficult. Even if you send that LED out to be tested, usually you can't find a lab that'll do like the instant on measurement. It's going to be after like 30 seconds, and then it's going to be a different measurement than what the manufacturer would have told you. So hardware startup, at least for the love of all things good, know the flux bin of the LEDs that you're playing with in the lab. But if you're like a higher level manufacturer that makes luminaires all day long and you're buying hundreds of millions of LEDs from different vendors, usually you have a good relationship with that vendor, and then you can get characterized LEDs. That means, like before with the 1250 lumen LED that we used as an example, before you'd only know that that was in a K2 flux bin between 1200 and 1290. But if you get characterized LEDs, you're gonna have the exact manufacturing instant on measurement that tells you it's 1250. So it's much more exact. And then with that, optical engineers can back calculate to see the efficiency of the whole system. It's one of the very, very few things that I miss about working for larger manufacturers of luminaires versus helping hardware startups now independently. Now, flux is not the only LED binning that manufacturers do. Manufacturers also sort by chromaticity, which is the exact color characteristics on a plot of where these things fall. So not just 4000K, but more specific than that in X and Y. If you're wondering what X and Y is, this is X on a chromaticity plot, and this is Y. And this curve here charts out the black body radiator, and so all of these are like in Kelvin for the different ways that we call white. And so as we're decreasing the color temperature, we're increasing X. More X means more red generally. Now we scroll past all the many, many pages of lists of bins for different color temperatures and all that stuff. We get to this cool chart. This top one is spectral power distribution, and they show a curve for 6500K in blue and 3000K in red. Sometimes you'll see a curve for every single color temperature. They will be different, but here Cree is just giving us two, and you'll see this is blue on this side and red's on the other side of the spectrum. So wavelength is along the bottom. Those are the different colors. And radiant power is on the y-axis in relative percentage. So they're showing comparatively how much of each color there is in radiometric units here, not photometric units like lumens. As we saw on that color chart, the more red something has, the lower the color temperature. And so this is high on the red side of the spectrum, and that's the 3000 K. And then as we get cooler white, the 6500 K, you'll see that has a big spike at the blue side, and it has a lot lower at the red side of the spectrum. I got a question earlier about whether white LEDs emit UV light, and that would be around 400 nanometers or less, which is in the middle here. So really barely any at all. Part 7, LED datasheets. We can get through it. Now let's scroll down to relative flux versus junction temperature. Notice here, 100% relative luminous flux is at 85 degrees. I mentioned in earlier videos that sometimes LED manufacturers bin at 25 degrees C because it looks better and it's easier to take those measurements. But for Cree, for this LED, they bin them at 85 degrees C. So the 100%, nominal output is going to be at 85. So to make sense of this, let's take an example of what this 100% relative flux at 85 degrees C means. Let's scroll up. All right, let's look at this bottom row, where at 85 degrees C, we get 900 lumens, because it's a nice round number for the flux group H2. So, going back down. So that means at 85 degrees C, 100% would be 900 lumens. Now for that exact LED bit, if you were to lower the temperature back down to 25 degrees C, then you're gonna get a bump of 10% in that flux. So if 900 lumens is 100%, and we wanna go to 110%, we multiply by 1.1, and that means at 25 degrees C, 110% of the lumens would be 990. So we'll go from 900 here to 990 lumens when we lower the temperature, the junction temperature of the LED. But notice the other side of this chart. If you warm it up higher than that, then that lumen output decreases. Now let's look at this chart considering the relative luminous flux is normally given to you at 25 degrees C. So for this chart, that would be 110% over here. And if you warmed it up all the way to the highest temperature that they measure, which is 150 degrees C, that would be about 85%. So let's bring out the calculator again. That would be 110% minus 85%. That's 25% difference between 25 degrees C over here, and when you warm it up to 150 degrees C. That's a big difference. First of all, it's important to recognize that this happens, right? As you warm up your LED, as you warm up your hardware device, the LEDs are going to give out less light by a significant amount. And the thing too that you have to remember is that thermal management is important. So being able to dissipate that heat as it's generated as the LED is on so that it doesn't build up to a point where it's so hot that you're not getting enough light out of that LED. Or even worse, smoking it out when you go beyond the absolute maximum temperature. I guess then the chart would be 0% relative flux. Moving on. Next comes a few different charts of forward current versus forward voltage. And this part right here, let me zoom in. This part's really important because you want to know if you're driving it for a 3 volt LED or 6 volt or 12 volt. Then there's another batch of charts for relative flux versus current. So how much light we're getting out versus how hard we're driving that LED current-wise. And that's also for 3 volts or 6 volts here on the right side, or 12 volts. And this is a super important chart, especially for optical engineers, because this tells us how much juice we're actually getting out of our LED when it's powered on. Now, notice up here, this is very important, look for this. It says for TJ equals 85 degrees C for junction temperature at 85 degrees C. So just like the above chart, this is for 85 degrees C because that's how it was binned, but this will be different for each data sheet. Now, relative flux of 100%. If we follow that over to the line and go down, this is going to be your nominal forward current. So this is like normal forward current. And usually you want to design your illumination system to be able to work plus or minus around this nominal. It is possible to drive it all the way up here and get over 180% for this LED of relative luminous flux, or all the way down here and get around 10%, but it's not really super reliable or great for the LED sometimes to be pushing it all the way to these limits. And that's why you want to design your system around 100%. And if you actually need something way lower or you actually need something way higher, then you want to pick an LED where that around in that neighborhood is where that nominal is going to be. Usually you're only going to see competent hardware design use this high end of forward current if it's like flashing, strobing the LEDs. Scrolling down, we have more charts, and this one is on relative chromaticity versus current. So as the current changes, the color is also changes. And this CCX and CCY is that XY chart that I showed before. If color is important to you, you also want to pay attention to these charts. Now we get to spatial distribution. This is another super important one for optical engineers. I went over this in an earlier video and I showed the polar plot with like a circle distribution. And this is going to be a Cartesian distribution, but the same sort of plot. Same data, just like stretched out. So here again, notice these distributions, how much light we're getting out at every angle coming out of that LED is different if it's high density versus high intensity. So if we go all the way up to the top, if it has the dome or it doesn't have the dome for this specific LED, we need to know which one we're looking at. These distributions are similar, but the high density one, the one with the dome on top, is more Lambertian, and the high intensity one has kind of extra light coming out right through the center of the LED out at like 0, 1, 2, 3 degrees. So this high intensity one is really great if you're trying to get super tight beams that have more light right at these narrow degrees, because here's the degrees on the bottom, and like 0, 1, 2, 3 would be right there, right there. A better illustration of this would show like maximum candela, I guess, for that 0 degree mark, so that you could see that I do believe, but I'm not 100% sure, but I'm pretty sure that for the high intensity one, this 100% coming out at 0 degrees is going to be higher than the 100% coming out at 0 degrees for the high density LED. So the amount of light we're getting out at these 0, 1, 2, 3 degrees is going to be a higher number, even though we got it in relative percentages here, so it's hard to see from these charts. So if you have a lens or a reflector that you designed around this high intensity one, because you want like a really tight beam or really powerful 0, 1, 2, 3 degrees coming out of your illumination. If you try to play a fast one and switch out that high intensity LED for this high density one, people are gonna know. Beam most likely will not be as tight. It won't be as narrow of a beam distribution, and you probably won't get as high intensity coming out of that center. So don't do it. You've been warned. Then we have some charts for thermal design, and this is why it's really great to have someone who's an expert in thermal management, because I'm not. I just know don't make it burn. But if we just try to read the chart and understand what it's saying, this is ambient temperature on the bottom. So that's the environment that your hardware device is in. And as that temperature increases, the maximum current that you can shoot through that thing decreases, assuming you don't want the LED to die. After that, we get back to luminous flux performance groups. These are the flux bins. And I talked about this in an earlier video, so I won't do that again, but this is where you find it. And also the chromaticity bins. Those are coming through again. Then we get to order code and bin code. And I'm sorry, Cree, but This is still confusing to me. It's not always entirely obvious if you're looking at a number and it's the order code or if it's the bin code, so you kind of have to play a riddle game to figure it out. I'm not going to go through it, but this is where you would go to play that game. I believe order code is what you would find like if you're trying to order the thing on DigiKey or Mouser or whatever, and then that only shows the minimum flux group that it could be. But then over here on the bin code, which is what you might find on a sticker on the actual package of LED, that's where you might find the specific luminous flux group. So don't throw away your packaging, it's very important. Part 8 of LED Datasheets, let's finish off looking at this Cree LED, and I might do some more in the future on other brands just because I don't want to show favoritism, because this was not sponsored, but it could be. But it wasn't. I would not be opposed to the idea. And just so we're clear, this was sponsored by SpireStarter.com, which is my company where I do optical engineering of illumination and other non-imaging things like IR sensor optics, reflectors, lenses, all that type of stuff. So the only huge thing left on this data sheet in terms of optical engineering would be this schematic of the actual shape and size of these two different LEDs. For designs that need high precision, it's good to be able to model the actual physical LED, not just the ray file, which I'll get to in a minute. But if you're not an optical engineer, but you're trying to pick out a source before you've spoken to one, know that this shape is very important to optical engineers, because the smaller the size of the light emitting surface, the easier it is to control that beam. The more control we can have over the shape of the light coming out for a given size of optic. What do I mean? Well, if you're working with a teeny tiny LED and that works with a teeny tiny optic, if you move instead to an LED like this size, then this size optic is not going to work anymore. To get the same control as with this system, you would need an optic that's much bigger. And usually that's not something product managers like to see. So getting the smallest option possible is not a trivial advantage, even sometimes to tenths of a millimeter, depending on what you're trying to do. But it's not the overall size of the LED that you have to care about, it's the light emitting surface. Usually that's gonna be, if it's like a white with phosphor coating, it's gonna be the yellow part of the LED. Light emitting surface is often abbreviated to LES. You might see that on optics, so like if you're looking for a lens and they have it simulated with a specific LED, then it might say with an LES of 5 millimeters, and that would be a light emitting surface of maybe 5 millimeters in diameter. If it were this one, so it's not going to be the whole white part of the square, it's just going to be the yellow part. That's the light emitting surface. It's the surface that is actually shooting out light rays. So oftentimes when electrical engineers are put in charge of picking an LED based on wattage requirements, that kind of pins me in a corner as an optical engineer on what I can design. Sometimes they have such a huge array, COB, that you can't get the beam shape out of the size of the luminaire that you're given to work with. If you want to get super deep into this, look up the word étendue. If you're a masochist, you can do that. The last thing I want to mention isn't even on the data sheet, but if we scroll up higher back to this spatial distribution, this is what shape the rays are coming out of the LED at. Is it like this or is it like this? These plots are nice, they're great. They give you a general idea of how these two LEDs are different. But if I want to model this LED in an optical simulation, there's a problem. How many data points can you pull off of this curve? 1 or 2 dozen, maybe 3 dozen, maybe 100, maybe 1,000 even, right? 1,000 points pulled off of this and turned into a model of an LED in your optical simulation. That might seem like a lot, but it's still just going to be an approximation of where the lights are landing really far away. For most optical systems, you don't want to just have this to model the spatial distribution off. You can get by sometimes if it's a lit effect, like a light pipe or LEDs behind a diffuser panel. Sometimes you can get by. I've done it before and it's worked all right. What you really want is array file, and you need to go to the actual manufacturer's product page, not on DigiKey, not on Mouser, to find these. So for this specific LED, Cree doesn't have the type of ray files for my simulation software, which is Light Tools. They have it for ProSource. So I would need to ask them to generate a ray file specifically for my simulation software to be able to really accurately model this LED in a simulation. That could take a while. But let me show you the difference between the amount of data you can get from this and this ray file, which is really similar to the LED that we were looking at from Cree. These dots are rays, and there aren't 10 of them, there aren't 3 dozen of them, there are not even 1,000 of them, there are 5 million dots. If we want to see what those look like, let's run a simulation. Oh my god, there's so many! 5 million rays is much more than 1,000, or way less than that. The data that created this model came from an actual LED that they measured and took lots and lots and lots of really tiny measurements all the way around this thing out. This is a ray file. This is important. It's also the kind of thing that you're not gonna get if you get a super discount LED from like Alibaba, from a Chinese vendor that's like not a name brand. They're usually not gonna have that. So if you're a hardware startup and you want to eventually build something that has 1 million of these things or even a few thousand of these things, and you build a system around this LED, there's only so far that you'll be able to optimize it unless you take that source and you send it out for a measurement, which is going to take a lot of time and a lot more money than you were probably anticipating. So if you're using an LED in a hardware project for a light source that needs like a reflector or a lens, and it's not just a diffusing indicator light, get one that has a ray file already. It's better to go with the name brand in the long run. Because once you reach a point where you want to bring in an optical engineer to fine-tune that design, there's only so much we can do with a few data points versus millions. There you go. Now you understand most of the important stuff for an optical engineer, at least, on LED datasheets. If you need some one-on-one consulting about your Illumination or IR sensor, you can go to spirestarter.com, go to book me, and then you can immediately schedule a 20-minute free consultation with me, and we can talk about what I can do in a long contract. Or if you don't have the time or budget for that, then you can just schedule a 90-minute consultation, go to the burger thing, and then go to book consult, and you can get up to a 90-minute Zoom meeting with me immediately booked. You can send me your NDA right through.